questions about anything at all before we get started today? All right. Well, today we are going to practice all the stuff that we talked about on Monday and close out chapter 9 pretty much. We're going to look at everything that we already mentioned, and then maybe one more thing before the day ends. And then on Friday, we'll make sure everything from 9 sits good with everybody, and then also look at test review stuff before next week. To quickly glance over what we did on Monday, these are the concepts introduced. Chapter 9 is about pressure and buoyancy. To that end, we redefined density, just mass over volume still. The definition of pressure is force over area. So if something is pressurized, there is forces being exerted on the object's surface area. And again, that's really what your nervous system detects, because you don't detect force, you detect pressure. And on planet Earth, since we have a tendency to always be surrounded and immersed in fluid, we can calculate the pressure that that fluid exerts based on the density of the fluid and how much of that fluid is present above you. So on Earth, density of air times the height of the atmosphere would tell you atmospheric air pressure. For just useful number, I'm not expecting you to memorize this, but it comes up so much that you might end up anyway, especially if you hang out on the chemistry floor. So this is just the sort of thing that I would tell you if you absolutely needed it, but this is just atmospheric pressure in units of pascals. It'll come up occasionally on your homework, especially if it asks about atmosphere or true pressure. Real quick though about this formula, there's something about it I want to mention that I meant to do on Monday. Main point here is that pressure increases with depth, and you probably figured that from hearing about the ocean before, but also just comparing pressure down up, here to pressure on top of a mountain. To that end, have you ever noticed that dams tend to be shaped like this? Now, if you've never laid eyes on a dam, that's fine. I have happened to visit the Hoover, but in case you have not, here are some images of the Hoover Dam. This is the water side, and it does just go straight down. But on the other side, this is the dry side, notice that it does slightly curve out on the way to the bottom. I'm wondering if there's a more prominent shot here. Oh yeah, here we go. The wall curves outwards as you head down. And that is to deal with the fact that water pressure increases with depth. The side with the water is flat, but that bottom part has more force on it, on the flat area of that part of the dam, so they physically just thickened the opposite wall to keep it from, breaking. So, if you ever visit the Hoover Dam, that's why it's shaped that way. Also, if you ever visit the Hoover Dam, I don't know if you're allowed to do this, but someone did it anyway. Someone dropped the basketball from up here, and combination of giving the ball spin and the curve, as long as the ball spins, it actually kind of sails outwards. So, 2 consequences of the dam being shaped that way. All right, that's just a couple applications of this particular formula. The other thing we talked about was buoyancy. Buoyant force is calculated by fluid density times the volume of the submerged object times 9.8 on planet Earth. And basically, if you're submerged in a fluid, the upward and inward pointing forces on the lower part of you is greater than the inward downward pointing force on the upper part of you, because pressure increases with depth. And as a result, since the upward force is slightly stronger than the lower force, net force up, buoyant force, you're lighter in a fluid than you are when you aren't. And main thing we're going to start with today is just utilizing those formulas and concepts and a few more examples to make sure that they
just stick before we close this week out. So any questions or objections before any of that? Yes,
I have a random question.
by all means.
Okay, so let's say that there's like a swimming pool being held up by ropes, like the four corners, and it's filled with water, and there's a whale inside. Would the whale or the weight come from the water or from like the water and the whale?
Okay, so let's see here. Whale. All right, so there's our pool, suspended from ropes. Now, okay, actually, I'm going to redraw the ropes slightly, just for simplicity. All right, I've drawn it this way so that there is one vertical rope holding the whole weight of everything. This rope, this one vertical rope, the tension in this rope would need to be strong enough to hold the weight of everything below it. Because if that rope snapped, all of it goes. So that rope would be holding the weight of the physical pool, the water, and the whale. All of it. The pool itself, like, you know, the bottom low part of the physical object has to support the weight of both the water and the whale. The whale, whale would be fine as long as nothing breaks. The whale would just, things would be normal for the whale. But the ropes itself would have to support everything. Does that answer the question?
Mm-hmm.
Okay. Yeah, because everything connected beneath it, its weight is being applied at that one point. Just because the whale is floating doesn't mean that its weight stops. It's basically, since it's pushing down and out on the water is going to be pushing, you know, an equivalent amount on the whole system. Like its mass is still present.
And it would apply if there were more, it would just be weight distributed between the ropes?
Right. If instead of one rope, it was divided up like I first drew it, it would just be evenly divided between all the ropes. Interesting question. It would take a lot of helicopters to try to move around a pool like this. It's a good thing whales don't end up inland very often. Actually, when they end up beach, it's usually easier to put them on a flatbed truck than it is to try to airlift them. Anything else on your minds? All right. So I try to come up with some examples kind of similar to your homework problems, just so that you're ready for them when you're working on them. Rather than taking the whale out of the ocean, we're going to put something in the ocean. Two things, actually. First up is a sea drone. Basically just, you know, remote control camera that can go underwater instead of in the air. And given that electronics don't like water, we've had to seal all the electrics of this particular drone inside of a glass sphere. So all the circuits and stuff just go in there to keep them dry. Now, water pressure, sea pressure is kind of a pain. So we have to make sure, if we're the ones building this thing, that this is as durable as possible, that it is watertight, and that it is not, that it is going to be able to handle the pressures down there. But we need to know what pressure it can handle so that we can write on it, you know, do not dive below this depth for legal reasons. Basically, any device that is waterproof, it's really just rated waterproof at a certain depth. Because the deeper you go, the bigger the pressure, the harder the water is pushing inside. So even those waterproof watches that someone will try to sell you, they always say waterproof up to a certain depth. So let's figure out the depth that this thing is waterproof to. The glass dome of this particular object has a surface area, so the area of the exterior of the sphere, not its volume, but its area, of 0.75 meters squared and it is able to handle, or it will start breaking if exposed to a compressive force of 30,000 newtons. So if you took this thing and squeezed it inward with a net amount of 30,000 newtons, it would crack. For context's sake, that is about 6,500 pounds, which is, just a little more than 3 tons. So you could hypothetically drive a tractor over this thing and it might be fine. So it's a good durable sphere. We need it to be durable for this purpose. Now my first question is, assuming that it is pressurized at sea level, so normal atmosphere is pressurized 0, no extra strain, it's what it's built for, is being on the surface. What additional pressure will break it? What pressures can this thing dive to? Answers. 40,000. Very good. Pressure is just force over area. So we take the compressive force that it can withstand, divide by that area, and you get 40,000 pascals. Which sounds pretty good. That's, 4/10 of atmosphere. So that's the pressure it can, that's the lowest you'd want to go. Actually, frankly, that is probably the pressure that would start cracking it. You wouldn't want to really be exposed to this. You'd want to stop just short of this. But if that is the extra pressure that is the danger zone, what depth in the ocean would this thing start struggling at? Wait, 3 point. The decimal point is one place over. Or I think it is. Hold on. So that is the danger zone extra pressure level. Under the water, that pressure is going to be caused by your depth within the density of seawater. So 40,000 equals density of seawater, slightly denser than fresh, times 9.8 times, H usually stands for height, but it means height of fluid above you, which correlates to depth. Maybe I misheard what you were saying, sorry. Oh, no, you were right. I messed up. No, you're right. You were absolutely right. My mistake, sorry. Yep. 4 meters. Which for context is about 13 feet deep. It's not a lot. This sphere could hypothetically be run over by a tractor and be fine, but if you take it 13 feet underwater, it's going to start breaking and leaking. Pressure's powerful. And it's why if you build something designed to be used underwater, you have to be very careful, especially deep underwater. Submarine construction is a nightmare. Once again, if you ever own a waterproof watch, be sure to check what depth it's rated for. There's one more question here. First of all, any issues finding that depth? All right. Now, last up is the true pressure at that depth, and this is just a vocab term that'll show up once or twice on your homework. True pressure is the total pressure once adding atmosphere back on. So if you're ever asked for true pressure, pressure true, that would be pressure atmosphere plus, I would say, pressure extra. So, let's take normal atmosphere, add our 40,000 to it, and that'd be 141,325 pascals, which is only an increase of about 40%, just 12 feet under. Now that is salt water. A freshwater pool would be, you could dive a little deeper in freshwater because it's less dense. But water pressure is scary. Feet under, and you've already, actually no, I guess 24 feet down, and you've already doubled the pressure that's supposed to be on your body. No, not 12. About 30 feet down, you've doubled the pressure that's supposed to be on your body. And my ears start hurting at the bottom of a 12-foot deep pool. Any questions or issues with this one? All right. Next up, I got a buoyant force question. Submarines are way better at handling deep depths. The way that they work is they have tanks that normally are filled with air when they're on the surface, and when they want to sink, they will take the air out of those tanks, suck it into an even more pressurized vessel, and fill that tank with seawater instead. And this has the net effect of basically increasing the density of the overall ship. I'd say more accurately, it's increasing the weight of the ship to the point where if weight is bigger than buoyant force, the ship sinks until the two equalize. And you can control depth by just controlling how much seawater you've taken in. If you want to go deeper, you just pull in more seawater. If you want to rise, you eject some of that seawater. So submarines operate by having absolute control over their pressurization and how much extra water they've taken in. But this submarine, we're going to park it on the surface. So it's basically just going to act as a boat for the time being. here's our very poorly drawn submarine. Sticking part way out of the water. That'll become relevant later. As with most boats and icebergs, most of it is under the surface. And this particular tub has a mass of 43,000 kilograms. So it's definitely not floating because it's light. It is made out of metal. So, how much buoyant force is required to make this thing float?
43,000 kilograms per meters cubed.
Not quite. We do need its mass, though. We do need its mass. Because, well, our formula for buoyant force requires we know the volume of the object, which we don't have yet. So, we can't use this to determine buoyant force. Instead, my thought is, if this is its mass, how much buoyant force is required to hold it here at the surface? And a related question, what is the current net force acting on the submarine if it's sitting stationary here at the surface? If you were floating, stationary, what is your net acceleration?
0.
Yep. And if this thing is floating unassisted, not going anywhere, how many forces are currently acting on it?
2.
Just 2. Gravity down, because you cannot escape that, and buoyant force up from the water. So as long as you are floating unassisted, nothing interfering, and these are the only 2 forces present, they must add up to 0. Therefore, if you are floating unassisted, buoyant force is equal and opposite to the weight. So if you can find the weight, you can find the needed amount of buoyant force to negate it. Which in this case happens to be about 421,400 newtons, which is about 50 tons. Again, it's not floating because it's light. These things are, I assume, made out of steel. So, it weighs 50 tons, and it requires 50 tons of buoyant force in order to hold it up. If, when you were a kid, you ever asked someone how a metal boat floats, or perhaps if a child ever asks you, how does a metal boat float? If you had a solid block of steel that weighed that much, it would have a certain volume to it. But if you use that block to build an entire boat, the whole thing has a much bigger volume for the same weight. So the net density is lower. Because, the submarine isn't a solid block. You turn it into panels and mold it into this shape, or, A shape. I'm not good at art. So, ships float, even metal ones, because it takes up more space than a solid block that weighs the same thing would take up. So that's the answer if a kid ever asks you that. So that's the needed buoyant force. Next question then, what is the volume of boat underwater to make this happen?
The volume of the boat underwater, so the part that is underneath the water?
Yep.
Half of the volume that's above.
Not quite half. 1/5 of it is above the water, which means that 4/5 of it is underwater. But first question is just, what is the volume that is underwater? And conveniently, that is exactly the volume in the buoyant force formula. Because what this formula cares about is only the amount of the object under the water's surface, because that's the only part of it that is displacing any water. The part that's above the water may as well not exist. The water doesn't know about it, the water doesn't care about it. Only the part that's beneath the surface does. So V object is actually what we want here. And since we kind of found buoyant force in a roundabout way, now we can solve for it. Density of seawater, which is slightly denser than fresh. It's not a big difference, but notice that there are bigger ships on the ocean where the water is denser and where it's easier to float than, like you don't usually see battleships in lakes. And that should give us a submerged volume of 41.95 meters cubed approximately. Bless you.
Thank you.
Note again, that is just the amount under the water, and that takes up way more space than the same weight of steel would if it was just a solid block. Now, when I was actually a physics major at this school, a Navy officer came by one day to try to convince us to enlist in the Naval Nuclear Submarine Program. They pay you a lot of money to live on an irradiated tin can underwater, basically. And it's a good amount of money. However, one, you're stuck in the tin can with the nuclear reactor and all of its waste. Two, I'll point out that 42 meters cubed of living space isn't that much. A meter cubed is this by that by that. So 42 of those cubes stacked into a livable area. And you don't even have access to all of that living area because most of it is made of water, walls, machinery, and the nuclear reactor. So it's not a lot of living space. So I said no. But any questions or issues arriving at this answer? Yes.
Are we assuming that's 4/5 of it?
Yeah. This is just what's under the water. And if 1/5 of it is above the water, this would be 4/5 of the total, which we could actually use to our advantage to figure out what the total is. Whatever the total is, 4/5 of it is that number we just found. Therefore, if we take that 4/5 and send it over to the other side, effectively multiplying the answer we just got by 5/4, you'll find the total volume of the entire thing, which if you were building the stuff, you'd need to know the entire volume since at some point the entire volume will be underwater. So the whole thing, factoring in what's currently above water, is about 52.5 meters cubed. So that only adds about 10 meters cubed to your living situation, which again, you don't have full access to because it's mostly metal walls and equipment. Questions?
Yes,
Okay, this is not related, but
by all means.
you said that submarines can control their pressure, right?
Mm-hmm. They control the pressure inside, well, one, you have to control the pressure inside of the human space, because you need the air in there to be the same pressure as the surface. Two, they can control the pressure inside of the saltwater tanks and inside of the air tanks, because if the reservoir is normally full of air, they have to pressurize it in such a way to then remove that air and put it into a different tank to make room for seawater.
So why did the millionaires die?
So, not core syllabus stuff, but, current events. Some of the news articles about that kind of pointed out that the guy in charge of the company probably took a lot of shortcuts on development because he really wanted to get the thing built and functional to start making money off of it. And money was definitely the prime motivator. It sounded like from some of these articles that shortcuts were taken and things were not tested super thoroughly. Also, the body was made out of carbon fiber, which, while strong, handles pressure differently than the parts of the sub that weren't carbon fiber. And so, if different parts are handling the strain differently, parts of it will warp at a different rate than others, and the net amount of effect on the vessel gets weird because of that. So, shortcuts taken. The exterior of the ship was not made out of one solid type of material, causing parts of it to compress at different rates. All those things combined led to a bad time, among other factors that I might not be aware of. Ironically, the Logitech controller probably was not the problem. To answer the question. Any other thoughts? All right. Well, there's only one more concept related to pressure that I want to talk about, and it's kind of just jumping straight off from the pressure formula. And I'm under the impression a lot of my students spend a lot of time on the chemistry department for your majors courses, so I'm going to start explaining this through what I feel like is a more common chemistry application of pressure. When I took chem classes, I feel like pressure was often used when talking about, say, the pressure of a gas inside of a container, which may be subject to things like temperature and moles of gas and things like that. And if a vessel is pressurized in such a way, the gas is going to be exerting outward force on the internal surface area of the container, correct? Now, I'm trying to draw basically a Party City helium tank. This has a pressurized gas inside. It's thankfully a non-flammable one. And it's pressurized so that it can contain more helium than it's supposed to. And because it's pressurized, the helium exerts force outward on every internal piece of surface area inside of the tank. Sound familiar so far? All right. Now, the same pressure can create different forces on different surface areas. And if we consider the different walls of this container to be different objects with different areas, like if we're assembling it from different pieces, the flat circular bottom of this tank has a bigger surface area than the flat circular cross section of, say, the nozzle at the top. Different surface areas, and that means that the same pressure will create different forces on the two different parts. And since this area is smaller, there's less pressure up here, so the parts up here tend to be smaller. Like the one nozzle is usually not as thick as the walls of the rest of the container. It doesn't need to be. Whereas this piece down here, this piece of metal is usually pretty thick.
along with the rest of the side walls of the container. That's why those things are a pain to move. The helium doesn't weigh that much, but the metal of the tank does. So they're heavy even when they're empty. But the same pressure creates different forces on different areas. Now that pressure is still constant throughout the entire container. So, you know, the pressure down here is the same as the pressure up here, P1 equals P2, but those different pressures exert different forces on different surface areas. And so you can get some interesting scenarios where a system that is pressurized can have different forces applied to different parts of itself. This is called Pascal's principle, and again, that formula is basically just saying that the pressure is consistent throughout every part of the system, but that doesn't mean the force is the same across every area, every part of the system. And humans have figured out some interesting ways to take advantage of this over the years. I'm going to ask what might feel like an odd question. Can any of you deadlift a car? So maybe, hypothetically. I can't. I know that I can't for a fact. So if I ever needed to get my car in the air, that would be a problem. However, utilizing this, I can show you a way that you, with mostly your bare hands, can lift a car.
So is that the hack to the distressed mother with the baby over?
Not quite. That's more to do with biology and psychology. What I'm about to say is purely physics.
Yeah.
But, you know, what's the term? Adrenaline, but there's it's not rage strength. Ludicrous? No. There's a term for it, but that's not my forte. There's a term for when that drive, that needed strength kicks in. But anyway, this is a system that can lift a car. This is the sort of thing that might be built into the floor of an auto shop. And you know, car shops are the types of place where you need to be able to get a car into the air because you got to see, you know, everything that's under it. And if you as a human can't do that with your bare hands, you need some technical assistance. So they have rigs that lift the car for them, and this is one type of rig that can elevate that car. This system, it's called a hydraulic system, if you've heard that word before. And basically this is just a series of tubes with liquid inside of them. It's not necessarily water, but I'll just say water for simplicity's sake. A series of tubes with water in them. There's a reservoir filled with water down here, and there's two vertical tubes sticking out of that reservoir. And those two different tubes have very different surface, cross-sectional surface areas. We got one thin tube over here and one very thick one over here. And each of those two tubes, they not only have different cross-sectional areas, but they also have cylinders, pistons basically, resting on top of the water that are able to push down on the water or possibly have the water push up on the surface of the piston. Now, I'm a visual person, and sometimes this two-dimensional drawing doesn't quite do it for my brain, so I'm going to try to make it a little more 3D, just in case that version helps you a little more. So here we have a very narrow cylinder connected to a large underground reservoir of, we'll just say water for simplicity's sake. And at the other side of that reservoir is a much bigger cylinder. So this is filled with water, and the water does extend up into these two cylinders. They're different diameters, and that means that they have different cross-sectional circular surface areas. So A2, A1. Basically, this circle is just physically bigger than this circle. Good so far? Okay. Now, each of these cylinders, oops, has a piston within it, which is really just another cylinder inside of the cylinder. Dang it. And the purposes of these pistons is, say, to have this piston push down on the surface of the water, and it's all sealed so that you are pushing down on the water so that it doesn't rush past it. You're pushing down on the water's surface. And liquids don't like being compressed. They have indefinite shape but definite volume. So if you compress water, it doesn't really contract, it just flows out of the way, right? And same is generally true of most liquids. That's why Phys1500 only works on gases. Gases can be compressed, the volume can change, they have indefinite volume, but liquids generally have a definite volume. Meaning that if you push down on the surface of this water, water's gonna flow out of this cylinder down into the reservoir, and then the only other place it can go is up into the other tube. And if the water level in here is rising, that water is gonna push up on the bigger cylinder, which again is sized so that water doesn't pass it, it just pushes up on its surface. And what this basically does is it takes your downward force from over here and sends it over here. You are pushing on the water, and the water is in turn pushing up on the other cylinder. So it's transferring the force from one side to the other. But it's not just transferring the force, it's gonna multiply it. Because when you're pushing down on this side, you are generating a certain amount of pressure, and that's gonna pressurize the whole system. The same pressure is gonna act on the other cylinder, but since it has a bigger area, that same pressure will create more force. Enough force to lift this car. So, the way that this works is, we're gonna apply a certain amount of force on the smaller side, and that's gonna output a different amount of force on the other side as it carries the pressure across. And this allows you to basically lift something very heavy with a very small force requirement. So, let's prove the math for this works. And first of all, any issues with the picture or the basic setup? All right. So the bigger cylinder has a cross-sectional surface area, so like the flat area of the circular part of the piston is 2 meters squared. So A2 is going to be 2. The narrower cylinder has a cross-sectional surface area of 25 centimeters squared. Since we like meters squared, what number should we actually write here? So how do we convert centimeters squared into meters squared?
Just gonna move the decimal places twice.
Yes, however, 100 centimeters to 1 meters. So normally you would divide by 100, but if you only do that once, you don't get rid of the centimeters squared, you only get rid of the square. So if you just do 0.25, that's not right, because that would be 0.25 centimeters times meters. If you're ever converting a unit with an exponent in it, you have to factor it equal to a number of times equal to the exponent. So here we have to divide by 100 centimeters twice to cancel out centimeters squared and leave us with meters times meters, which is meters squared. So instead of 0.25, it's 0.0025, because we had to divide by 100 twice. So there's a very big area difference between these two. My drawing over there is not to scale at all. Now, our goal is to find F1. That's the amount of force we have to exert to make this whole thing happen. So the next question is, how much required output force is needed to lift this car? We know its mass, and that means we can figure out its weight. And to lift anything, you have to exert a force equal to equal to or greater than its weight. So for F2, we're going to put in 650 times 9.8. So just the weight of the car divided by the area of the cylinder it's sitting on equal to the force we exert divided by the area of the cylinder we are pushing on. And again, it's the same pressure on both sides, but that's going to create different forces on the different sized cylinders. And overall, that should, I think that's it. Nice. Oh. Keep hitting the wrong buttons on the counter. Yeah. So, if you had access to this complicated hydraulic rig, you could lift an SUV with 8 newtons of force. That's less force than it takes to lift 1 kilogram. Which I think is cool. Questions? All right. Before we break, I will point out that there is a flaw with this system. Yes, it only takes 8 newtons of force on this side to lift the car on the other. However, the problem with this machine is that this cylinder would have to be like 100 times taller than the other one. And that's because the speed that this works at depends on volume flow rate. And since this cylinder is wider, because it's wider, this cylinder's volume, basically, sorry, rewind. The cylinder's volumes would need to be the same. And since they have different diameters, this one would have to be a lot taller to have the same volume, right? Basically, if you're pushing water out of here, only this much water is going to flow during that process, and that much water isn't going to raise the other side up as much when the other tube is just physically wider. So if this was literally how you built it, this cylinder would have to shoot like 800 feet in the air, and you'd have to be pressing down on it for that entire 800 feet. So when they build things like this, they have to take that into account and be very clever about how they deal with that. They have to get the ratios right so that the size on the other side isn't absurd. But it's pretty useful. And actually, you may not go to an auto shop very often, but if you drive a car pretty regularly, I will just point out that This is how your brake pedal works. When you push on the brake pedal, you are pushing in on a fluid and it's outputting force into the wheel drum. That's what brake fluid is. It's the fluid inside of this hydraulic system. And if you don't have brake fluid, pressing on the pedal's not going to do anything because then there's no fluid pressing, on the brakes. So, get your brakes checked. And that's how hydraulic systems work. Pneumatic systems do the same thing, they just use gas instead of liquid. Any questions? All right, well, that's pretty much it for chapter 9. On Friday, we'll review any chapter 9 stuff and also look at test review stuff ahead of the test next week. Let me know if you guys need anything. Have a great day.
Is the test next week or is this test review next week?
Both. Lecture next week is test review, the test happens during lab time.
Fair.
So even if you take it Monday, there's a review session first.
Out of curiosity, which one of those times is for this class?
I think technically the middle one is, but you can choose any of the three, because it's the same exam 3 times. I don't care when you show up. I'm gonna be here for all 3 of them.
Okay. Gotcha. Okay, thank you.
You're welcome. Oops.